Now we are going to start a new module. It is all about alcohols and phenols. So here, as you know, an alcohol is a compound that contains an organic moiety and an OH group, hydroxyl functional group. And normally, as you know, alcohols are of different types. That means the primary alcohol, secondary alcohol, tertiary alcohol, and also more than one OH groups are what are called polyhydric alcohols. Okay, and then normally when we talk about an alcohol, that will be a aliphatic hydroxy compound. Okay, so now let us discuss the methods of preparation of alcohols. Alcohols can be prepared from alkenes. The first method is by acid catalyzed hydration reaction. So here essentially the reaction is hydration. That means the addition of water molecule across the carbon-carbon double bond. Here alkene reacts with water in the presence of acid as catalyst to form alcohol. So here a molecule of water is there and an alkene is represented here, C double bond C. In the presence of an acid, the water molecule got added across the carbon-carbon double bond. Okay, so here we get a hydrogen of water and OH hydroxyl group of water, and we get an alcohol. For example, when we take ethylene or ethene as an example, addition of water in the presence of acid catalyst, then we get ethanol, CH3 CH2 OH. Okay, so in the case of an unsymmetrical alkene, for example, when we take an unsymmetrical alkene like propene, the addition of water takes place in accordance with Markovnikov's rule. Okay, so here the addition of water is taking place in accordance with the Markovnikov's rule when we take a unsymmetrical alkene. Markovnikov's rule says that the hydrogen part of the polar reagent will go with carbon contain more number of hydrogen atoms. So here you can see that this carbon contains more number of hydrogen atoms. Here we have two hydrogens and here we have one hydrogen. So the hydrogen part of water goes to the carbon that contains more number of hydrogen. So here it will be CH3. Okay, so here we are getting propane 2-ol, that is the major product. Okay, so and when we compare another example, CH3 CCH3 double bond CH2, addition of water is taking place, so the hydrogen will go with this carbon because it contains more number of hydrogens. Okay, and then the OH will come on this carbon atom. Okay, so here we get CH3C, CH3, CH3, OH, 2-methyl propane, 2-ol. So this is the major product. Next reaction is by hydroboration oxidation reaction. Hydroboration reaction. So likewise, when we use diborane or borane, we can synthesize alcohol. Okay, so here diborane reacts with an alkene to give the corresponding trialkyl borane as addition product. This is oxidized by alkaline hydrogen peroxide to the corresponding alcohol. Okay, so initially when an alkene like C double bond C compound reacting with a diborane, then it forms a trialkyl borane intermediate, which is on reaction with hydrogen peroxide. Oxidation reaction will take place, hydrogen peroxide in alkaline medium, then we get an alcohol. Okay, so here in case of propene, when we take an example, propene reacts with the diborane to give tri-normal propyl borane, which upon oxidation with alkaline hydrogen peroxide gives propane 1-ol. The reaction scheme is shown here. Propene is represented here, CH3 CH double bond CH2. It reacts with the diborane, BH3 twice, half BH3 twice, diborane. So here the first molecule of diborane will give a intermediate compound like this, CH3 CHH CH2 BH2. The BH2 part has gone to this carbon atom and the hydrogen of this borane will go to this carbon atom. Okay, and this is further reacting with one more molecule of propene, then we get dipropyl boron hydride. Okay, and if it reacts with one more molecule of propene, then we get tri-normal propyl borane. Okay, so which is on hydrolysis, then we normally get an alcohol CH3CH2CH2OH propane 1-ol. Okay, so this is an excellent method for the preparation of alcohol. It is seen that the addition of borane to the double bond of the alkene takes place in such a manner that boron atom gets attached to that sp2 carbon atom of the carbon-carbon double bond, which carries a greater number of hydrogen atom. So here, when you look at the reaction, here you can very clearly see that the boron part of diborane will normally attach with the carbon atom having more number of hydrogen, and that part will become converted into hydroxyl alcohol. Okay, so wherever you can see the B, boron, then that part will be an alcohol. So here, in fact, the addition of water across the carbon-carbon double bond is taking place in contrary to the Marconi-Coase rule. Okay, so thus effectively the alcohol formed appears to be formed by the addition of water to the alkene in a way contrary to the Marconi-Coase rule. Okay. So now let us discuss other reactions. Propene reacting with diborane B2H6, we get an intermediate tri-normal propyl borane, which is on oxidation in the presence of hydrogen peroxide in alkaline medium. Then we get a propane 1-ol CH3CH2CH2OH, and this product is anti-Marconi-Coase addition product. Okay, and then when we take cyclopentene derivative, 1-methyl cyclopentene in diborane and hydrogen peroxide, alkaline hydrogen peroxide, then we get trans 2-methyl cyclopentanol. Okay, so when you look at this kind of compounds, there is a stereochemistry involved in the product, in the reaction. Here you can see that the alcohol formed has the addition of H and OH from the same side. Okay, addition of H and OH from the same side, so we normally call it as a cis addition, but the product formed is a trans 2-methyl cyclopentanol. That depends on the type of other substituent present on the other carbon atom of the carbon-carbon double bond. Okay, so when you take another example, 3,3-dimethyl but1ene CH3C CH3 CH3 CH double bond CH2 diborane and alkaline hydrogen peroxide, then we get a 3,3-dimethyl butane 1-ol. Okay, so here also you can see that the boron part goes to the carbon of the carbon-carbon double bond of the alkene of carbon atom having more number of hydrogen atom in the alkene. Okay, and then that part will become an OH group, hydroxyl group. On account of the anti-Marconi-Coase orientation and the absence of rearrangements, the method provides an excellent means for synthesis of alcohols, which are difficult to obtain by other methods. Further, the yield of alcohol in this method is very good. Okay, so that is a very, very important point in this reaction. The yield is very, very good. The next reaction is by oxymercuration demercuration reaction. So we may discuss this reaction in the fourth sem also. Indirect hydration of alkenes to alcohols. So this method is also can be used for the preparation of alcohols by converting the alkenes. Alkenes react with mercuric acetate, HgOAC, mercuric acetate in a mixture of tetrahydrofuran and water to yield hydroxyalkyl mercury compounds. Okay, hydroxyalkyl mercury compounds is called oxymercuration process. Hydroxyalkyl mercury compound is called oxymercuration reaction. The scheme is shown here. Alkene RCH double bond CH2 is reacting with water and then THF mixture, mercuric acetate HgOAC twice, and then we get oxymercuration product RCHOH CH2 HgOAC. Okay, so here what happens is hydroxy part has already added to it this carbon atom, and then the mercuric acetate part has added to the other carbon atom of the alkene. Okay, so this product is what is called oxymercuration product, and then this product own reduction with the sodium borohydride. Sodium borohydride, keep it in your mind, it's an excellent reducing agent. Okay, sodium borohydride in basic medium yields the alcohol. So in this reaction, it is what is called demercuration reaction. So during the reduction process with the sodium borohydride, we normally doing the reaction of removal of mercury part. Okay, demercuration. Sodium borohydride reduces the acetoxy-mercury group and replaces it with hydrogen. Okay, so this is oxymercuration product, and it is reacting with the sodium borohydride in alkaline medium. Then we get an alcohol. The oxymercuration mercury part has removed, mercuric acetate part will removed, and the hydrogen is added to it. So this compound is reduced, and then we get an alcohol. So this reaction is exactly taking place in accordance with Markovnikov's rule. The net result of two-step method called oxymercuration demercuration is thus an apparent Markovnikov addition of water. Okay, and it thus effectively constitutes the indirect hydration of the alkenes to alcohols with a relatively high yield. Why it is called indirect hydration method is because first one, the reaction that we have to make for the oxymercuration process product, and then second one is the removal of the mercuric part, that is the demercuration part. So that is why it is called indirect method for the conversion of alkenes to alcohols. So both reactions can be carried out in the same reaction vessel at room temperature. Okay, so first we have to make the oxymercuration product, and then further sodium borohydride has to be added to it, and then we will get the reduced product like alcohol. Okay, so when we take an example of propene reacting with mercuric acetate in THF and water, then we get oxymercuration product CH3CHOH, CH2Hg, OAC. And this oxymercuration product is reacting with or reduced with the sodium borohydride in alkaline medium, then we get propane 2-ol. So next method is from carbonyl compounds. Here carbonyl compounds are reacting with the Grignard reagent. As you have already discussed, these inorganometallic compounds, Grignard reagent reacts with the alcohol, reacts with the carbonyl compounds to form alcohols. Okay. So alcohols are produced by the reaction of Grignard reagent with aldehydes and ketones followed by acidic hydrolysis. So you are very well aware of this kind of reactions. The first step of the reaction is the nucleophilic addition of Grignard reagent to the carbonyl group to form an adduct. Okay, and then further second step is the hydrolysis of this adduct yields the alcohol. So reactions are familiar to you. Here, as you know, Grignard reagent is a highly polar reagent. So the alkyl part is negatively charged part, and it will attack the carbonyl carbon of the carbonyl group. Okay, and then we get an adduct, and this adduct on hydrolysis, this part magnesium halogen attached to oxygen part will become a hydroxyl group after hydrolysis. Okay, and the type of alcohols, primary, secondary or tertiary, produced depends on whether the starting carbonyl compound is formaldehyde or any other aldehyde or a ketone. So as we have already discussed, if we use formaldehyde as a starting material, definitely we will get a primary alcohol, and any other aldehydes when you use, you will get secondary alcohol, and if you use tertiary alcohol, definitely you will get if you use a ketone as starting material, definitely you will end up with a tertiary alcohol. Okay, so the formaldehyde reaction is shown here. Formaldehyde is reacting with alkyl magnesium halide, and then we get an adduct. So as we have already discussed in the Grignard reagent reaction, that here this is a kind of step-up reaction, or one carbon atom or additional carbon atoms can be seen on the product. Okay, than the Grignard reagent part. Okay, so the formaldehyde, when we have taken formaldehyde reacting with the normal propyl magnesium bromide, so initially we get an adduct, and then finally it will be hydrolysis, it will be converted into a butanol or a primary alcohol. When we take alcohol, any alcohol you take, any other aldehyde you take other than formaldehyde, then we get a secondary alcohol. Okay, so when we, for example, we have taken acetaldehyde as an example reacting with ethyl magnesium bromide, and this part will attack the carbonyl carbon, and then we get CH3, CH2, then this carbon CH, CH3O, and then this part MgOH, MgBr. Addition product, which is on hydrolysis, we get butane 2-ol or 2-butanol, that is the secondary alcohol. And then ketones react with the Grignard reagents to form addition products, which on acidic hydrolysis give tertiary alcohols. Here we have taken a ketone as an example, reacting with Grignard reagent, then we get an adduct, which is on hydrolysis, we get a tertiary alcohol. For example, here we have taken acetone, reacting with the methyl magnesium bromide, and we get an adduct, which is on hydrolysis, then we get the tertiary alcohol. Next reaction is by reduction of carbonyl compounds. Carbonyl compounds can be reduced to alcohols by catalytic reduction method, or also we can use the excellent reducing agents like lithium aluminum hydride or sodium borohydride. Okay, so here the aldehyde has taken aldehyde reacting with the hydrogen, and in the presence of a catalyst palladium, it is converted into a primary alcohol, and a ketone reacting with the palladium catalyst, then it is converted to reduce to secondary alcohol. And if you take a ketone and sodium borohydride, again you are getting a secondary alcohol. For example, when you take propanol CH3CH2CHO, propanaldehyde, hydrogen and palladium, then we get one propanol CH3CH2CH2OH. And if you take a butanone as an example, wherever you see the C double bond group will be converted into an OH group. Okay, so here hydrogen and palladium, then CH3, CHOH, CH2, CH3, butane 2-ol. So this is a ketone, and we get a secondary alcohol. And if you take another example, CH3 C double bond O, this is also a ketone, 4-methyl pentane 2-on, reacting with the sodium borohydride or a reducing agent, then the C double bond O group is converted into a hydroxyl group. Rest part will be the same. Okay, I am stopping here, and the next class we will discuss the chemical properties of